In the last video, we talked about pKa's of protic acids. In this video, we'll talk about pH of a solution. So we saw if we have an acid added to water, so generic acid added to water, some H3O plus ions are present and some conjugate base ions are present. The pH is a property of the solution, and it's equal to the negative log, this is base 10, of the concentration of just H3O plus ions. So remember, pKa's are properties of acid molecules. The pH is the property of a solution. pH is a property of a solution. This is a property that can be experimentally controlled. So if we're trying to increase a pH, now increasing a pH means we're becoming more basic, can add a base to increase the concentration of OH ions, decreasing the concentration of H3O plus, and that raises the pH of the solution. So if you're adding a base like OH minus, that could be in the form of sodium hydroxide, you'll raise the pH. So the solution becomes more basic. If you add H plus ions, like in HCl or some acid, this will lower the pH. Or create a solution that's more acidic. So follow similar pattern to pKa, where lower pKa, stronger acid, lower pH is more acidic solution, higher pKa, weaker acid, higher pH, more basic solution. When pKa's are determined, so this was talked about in the last video, a certain amount of each added, a controlled amount of each acid is added to a certain amount of water. And then we can determine pKa of that acid by controlling those amounts. When we're talking about pH, we can change how much acid is added, or we can change how much base is added to reach a desired pH. Or we can work backwards, determine the pH of a solution, and then consider how much base or acid was added. Now, if you have a certain pH of a solution, that can impact how an acid will behave in that solution. So there's really three possible scenarios. Let's say three possible scenarios with acid in solution. So let's say you add an acid that has a pKa that's equal to the pH of the solution. So pKa is 3, the pH of the solution is 3. Then in that solution, the pKa of the acid, the concentration of the acid added, so in its HA form, will be equal to the concentration of its conjugate base. So associated and dissociated concentrations are equal to each other, so this ratio is equal to 1. If we have a solution with a pH that is greater than the pKa of an acid. So now we have the acid that's added to the solution has a stronger acidity than the pH of the solution. So a stronger acidity than the solution. That means that acid, stronger than solution, it's going to dissociate. It's going to donate its proton. So the concentration of its conjugate base will be higher than its concentration of the associated form. So we'll say this ratio is certainly not equal to 1. Trying to erase this here. Okay, so this ratio will have higher concentration of A-, so this will be greater than 1. And this indicates that the acid exists more so in its deprotonated form. Deprotonated, we can also say dissociated here. So dissociated as in the proton has dissociated from the rest of the molecule. And then lastly, if the pH is much lower than the pKa, remember lower pH or pKa is more acidic. So if we have a more acidic solution than whatever acid is being added into the solution, the acid is going to stay mostly in its associated form because it's not as acidic as the solution. So this ratio will be less than 1. We'll have a lower concentration of the dissociated ion, the A-. So we can say acid exists more so in its protonated, but protonated just meaning its associated form. It's not getting an additional proton. It's just existing in its neutral form. So a better word for this is associated. So the acidic proton is still associated to the rest of the molecule. Now there's a limit here where if the pH is 2 or more units above or below the pKa, the acid is, quote, completely dissociated if the pH is 2 or more units above, or associated if the pH is 2 or more units below the pKa. Now remember, associated, or let's say dissociated, is deprotonated. The proton has left the acid. Or associated, that's like remaining protonated. So the proton has not been donated. Now I have completely in quotes because it's never completely dissociated or completely associated in reality. There's always some equilibrium, but we can treat it as being completely dissociated. All right, let's do an example question here. We'll say if ethane thiol is added to solution with pH of 12, what form of ethane thiol will be in highest concentration? Now we need some information here. We need the pKa of ethane thiol. Ethane thiol, by the way, is almost like ethanol, but with a sulfur instead of an oxygen. So thiols are similar to alcohols, but we've replaced the oxygen with a sulfur. So the pKa of ethane thiol is 10.6. So that hydrogen has a pKa of 10.6. So if we have an acid with a pKa of 10.6, we're adding it to a water solution with pH of 12. We have a higher pH than the pKa of the acid. So the solution is more basic relative to the acid, or we say the acid is more acidic relative to the solution. So that means that the ethane thiol will act as an acid and it will lose a proton, and this will be the form in highest concentration. So the solution is basic relative to the ethane thiol pKa. So the SH part of that molecule, the ethane thiol, will act as an acid. It will exist more so in its dissociated form. Now the pH is not fully 2 units above, so we still say that these two forms, I'm just going to draw a really long arrow here, are in equilibrium with each other, but the dissociated version is in higher concentration than the associated version. So we will talk about pH and pKa in context for the rest of the semester, so they'll become relevant in the different reactions that we'll learn in our future units.